Welcome to part 4 of data serialization. Let's talk about compressing the data. So first off, why? Why do we need to care about this? In early days, we probably did care about the amount of memory we were spending on this, and it could still be relevant, but it's much less so now that memory has become much more abundant. More important is the amount of time it takes to read and write this data. As we will be covering later in the semester, reading and writing the data is a major bottleneck, whether that's just in memory, or more importantly, if we're writing it out to a slow device like the disk drive. If someone has, heaven forbid, someone has a magnetic hard drive that we're saving to or loading from, that's going to take a significant amount of time. And worse yet, what if we have to send this serialized data over the network? The more data we send, the longer it's going to take, and we want that time cut down. So that means send less data. How do we send less data? Well, we compress it. We don't need to send it all if we can make it smaller. So a couple things we'll look at. First off, lossless compression. Lossless meaning it will be a perfect representation of the data, just in a smaller footprint. So we'll look at a couple of ways of doing that, and then we'll say that's not enough. Let's go for lossy compression, which means that we'll sacrifice some of the precision of the data in order to make it smaller. We'll have to be making a trade-off between what's good enough versus how big it is. So first off, let's look at a lossless compression, as in perfect compression, we'll use for sparse arrays. A sparse array is it's a big block of data, be it a matrix or an array, where the amount of data we actually are using is sort of limited, like most of the data is blank. For example, the name on the RoboCat. We had a name that was 128 bytes long, but we discussed it's fairly rare that a user will ever use all 128 bytes of the name. More likely, the name of the cat is going to be like Fred or Tom the Tomcat, right? Whatever. Like the name Tom only uses 3 bytes, but we have 128 bytes available for that. What we can do instead is to serialize it as if it were a vector of characters. Instead, we use that same technique. So we will start off by writing out an int, probably an 8-bit integer, to save space, how many characters are actually used, and then we will write out just those characters. So, for example, to serialize the name Tom, we will write out 3 and then T-O-M. So it took 4 bytes to serialize the name Tom, as opposed to 128 bytes to serialize T-O-M and then a whole bunch of zeros. Okay, that's the prefix technique, and I'm showing that mostly because that's what we did with vectors. The alternate approach, which is just as good, is to do the postfix or a null terminated string. So in that case, you would write out TOM0, again 4 bytes, and the 0 indicates this is the end of the string. So your choice of which way you want to do. I will note that in the case that all 128 characters are used, then you're actually going to have to write out 129 characters, because you have to write out the length and then all 128. And so you'll write 128 and then 128. So that's an extra byte. But that would be very rare that would happen, that someone used all 128. So once in a while, you'll spend a byte in order to save a lot of bytes most of the time. So here's the code version of that, where we do the prefix. We simply say, how long is the string in bytes, and then we'll write out the number of bytes, and then we'll write out those as bytes. Entropy encoding is sort of a more general case where we have some type of data that is rare and some other type of data that is more common. Now, the common data we'll see in the data stream very, very often, and so we'll end up repeating it over and over. We can leverage that fact to compress. For example, let's consider the RoboCat. The RoboCat had a data element called mLocation, and in this game, we have come to understand that the cats are usually on the ground when they're serialized. And that would mean their height, or y coordinate in this game. The y coordinate is almost always 0. So as we're serializing out the cats, we realize that the data has this pattern of going x0z, 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 over and over again. And then once in a rare while, it'll say xyz, that the y is not 0. So what we'll do is to leverage the commonness of that 0 to save that in less than 4 bytes. It takes 4 bytes to write out the whole float 0. What if we can just say, no, this is the common one, and just compress that to something smaller? For example, we will just write out the x and the z as floats, bang, bang, that's fine. But then when we get to the y, we'll say, well, hey, is it 0? If it happens to be 0, we'll just write a single byte for the value true. On the other hand, if it is not 0, we'll write false in that byte and then follow it with the 4 bytes that represent the actual position of the y coordinate. So we've used a single byte to indicate whether it is 0 or not 0. And if it is 0, then we've traded a 4-byte stream, like 4-byte float. We've traded that with just a single byte, so we made it smaller. On the other hand, if it was some non-zero value, we've increased it from 4 bytes to 5 bytes by spending that extra byte. The thinking is that in this case, most of them will be 0. So most of them will shrink and very few of them will grow. And it's even possible, depending on exactly what we're serializing and how we're serializing it, we could squeeze this down from a byte to just a bit, because we only need 1 bit to do this. So depending on how we're serializing, maybe we can squeeze it even tighter. Let's take a look at a concrete example here. How many bits if we do it for a bit, how many bits do we need? We need 1 bit for the true or false, and then 32 bits for a float. So in the worst case, for a cat that is not at 0, it would take 33 bits to save that data. Let's say, is that a win though? Is that a win or not? Let's say, for example, we measure the commonness. We'll have to go through and do a survey of how many cats are on the ground. Let's say we find 90% of the cats are on the ground. Then 90% of the cats take 1 bit each. And the last 10% of the cats take 33 bits. So that comes to an average of 4.2 bits per cat. Now, and that's kind of funny. 4.2 bits. How can you have 0.2 of a bit? How can a cat take 2/10 of a bit? That doesn't make sense. You can't have a fractional bit. It's because it's an average, right? Some cats take 1 bit, some cats take 33 bits. Nobody takes 4.2 bits. It's just on average, they average out to 4.2. Now that's the case if we do a bit at a time, which frankly is going to be a challenge. More likely we'll have to do a byte at a time. If we do it a byte at a time, then our 90% will take 8 bits and our 10% will take 40 bits. So both of them have increased, and that makes our average now 11.2. 11.2 bits per cat is still way better than 32 bits per cat. And so we've still gotten a win. We can extend the idea of entropy encoding even further. to take on data that we don't know about. We can analyze the data, look over the data without even knowing what the data is to see how common certain patterns of data are. Perhaps zeros are extremely common in this data, for example. This is pretty normal for zeros to appear in all kinds of data. So perhaps we can use an encoding to simply take advantage of that. For example, we can use Huffman encoding, where we build a lookup table of commonly appearing numbers, and then we'll just refer to that table when we get those particular sequences with a smaller amount. There's other types of encoding: arithmetic encoding, geometric encoding, run length encoding. RLE, or run length encoding, is very commonly used for images, for example, where you tend to have a repeated data element that's repeated very many times before it changes. Perhaps you have a solid block of one particular color, and then it changes to another color for a while, changes to another color. If you serialize those out just as colors, you'll see that it's going to repeat, and then change, repeat. So you can encode that tighter by just saying how many repeats, and then the value that repeats, how many repeats, the value that repeats. And there's different approaches for that kind of thing. Okay, the last one that I want to talk about is geometry compression, and that is when we are going to do a lossy kind of compression. This is not lossless anymore. A lossy compression is where we drop precision. For example, going from a regular image that maybe we run length encode, we could drop it to a JPEG, which I think you're aware is a lossy compression. It creates artifacts. It doesn't look exactly like the original image, but it's close enough while being a much smaller data footprint that might be advantageous for like web use. If we have to upload and download on the web, we want that to be small. Let's do the same thing, for example, with a quaternion. We know that the quaternions that we use in this class are all normalized. And that means the components have to square, and the magnitude, right, has to add up to 1. So that means if you give me any 3 components, I can tell you the fourth by just doing square root of sum of squares. All right, I can just take the x squared, y squared, z squared, add those together, subtract that from 1, and that gives me the w squared. Square root, I've got the w. So I can drop the fourth term of a quaternion by knowing that this property is true. And then what else can I say? I can also say that not only do they have to sum up to 1, but the range of each of those 4 terms is only -1 to 1. And I'm using a float for that. So I don't need those large values that a float can have. I just want the precision. And maybe I don't need that much precision. As these floats, what are these angles that we're describing? How precise do I need them? So what if I say, let's use a 16-bit instead of a 32-bit, and we'll use fixed point instead of a floating point. Because we don't need to say what the range is. Maybe we just need the fractional part of the angle in there. And so we'll just store the fraction. We don't need a float to just store the fraction. We use a fixed point notation, and instead of 32 bits, we'll just cram that down to 16 bits. So that'll cut the size in half right there. And if we drop the w using the x squared, y squared, z squared trick, we can get it even smaller. So that's data compression. In the next video, number 5, the last video in this series, we'll talk about maintainability, how to write your code in certain ways to make the whole thing a whole lot smoother for you. Okay, see you in the next one.